Okay, so the second part of chapter 7 is a calculation part. You will learn how to calculate the solidification time in a casting process. So first, we define the total solidification time as the time required for casting to solidify after pouring. So we have seen already together on the graph what is the total solidification time. So here you will add, you will consider that solidification will start just after pouring and will continue until you have complete freezing of your mold. So this corresponds to the liquid cooling part plus the change of phase part from liquid to solid. And the value of the total solidification time is determined experimentally. And we come up with an empirical relation that will allow us to calculate this time based on several factors. So first, mainly the solidification time, the total solidification time is function of two things. First, the properties of the mold. Okay, so we have what is called the mold constant, which will depend on the mold type, material type, and we have the geometry of the pattern. So we can see here that the solidification time is affected by the ratio of volume over area. And as expected, higher is the volume to area ratio, higher will be the solidification time. Because if you increase the surface of the lateral area, A is the lateral area. Okay, this means what is it is the area contact between the mold and your cast, between the mold and your final casting product. Okay, so A will take into account the total contact between area between them. So if you have, for example, internal and external surfaces, you should add them. Okay, we will see this in problems. So this is for the area, and for the volume, it's the volume of the cast. So for example here, let's say if you have a cylinder with a hole inside, okay, then when you calculate the total area, you should take the surface of contact with the core, which is the internal area, and you should take the external contact area also. So you will have to take into account these two parts because everything in contact with between the casting and the mold should be considered. And for the volume, so here, for example, if you calculate it numerically, if we have an inner hole of diameter di and an outer hole of diameter d out, then the area, the total area will be A equals to, what is the total contact area? Who will tell me? If I consider a length L of my casting, what will be the total contact area with the mold? So imagine what is the external area and the internal area. It's equal to what? First, the external area is pi do, it's the perimeter, times the length. Okay, times the length. This will give you the external area, and the internal area determined by the core is pi d inner times L. So this is how, in this case, you calculate the value of the area. Now, concerning the volume of the cast is simply here because you have a hole, so you should do pi d outer square over 4 times L minus pi d inner square over 4. So this is how you get the volume. So you can see that the solidification time is function of the mold properties and the geometrical properties of your final pattern. Okay, so we can say that in this case, the value of n, okay, it's determined experimentally, and in general, the typical value of n is 2, and the mold constant will be given function of the mold type used. Okay, So we can see that the solidification time will increase with the mold constant, will increase with the volume, and will increase with a reduction of the contact area. Okay. So if I decrease the contact area, it is not good because I will need more time to solidify. So what we try to do, we try to optimize this. We advise to have a low volume to area ratio in order to reduce the total solidification time. Now, uh, how to determine the mold constant? The mold constant is determined experimentally and it depends on several factors. As we said, it's related to the mold properties, so it will be affected by the mold material, the thermal properties of the casting metal, and also the pouring temperature relative to melting point. So it's due to several factors concerning the mold characteristics, also the properties of the casting metal, because we have here heat transfer between the mold and the casting metal, and we have it's also related to the pouring temperature relative to the melting point of the metal to be cast. Okay, so these factors will affect the mold constant, and the value of Cm for a given casting operation can be based on experimental data from previous operations carried out using same mold material, same metal, and pouring temperature, even though the shape of the part may be quite different. So look, in order to have same mold constant, we should satisfy the following condition. We should deal with the same mold material, same casting metal, and same pouring temperature. If these three are equal, then even if you change the geometry of your pattern, Cm will remain the same, because Cm is independent of the geometry of your pattern. It's dependent on these three factors. This is why sometimes if we determine Cm experimentally for a certain casting process, even if we change the geometry of the pattern, if we keep the same mold material, same same metal, casting metal, and same pouring temperature, then Cm will stay the same. What will change is the ratio V over A, which will affect the total solidification time. Any question on this? Now, Shrovinov's rule is the one we introduced together. And this rule will tell us the following. A casting with a higher volume to surface area ratio cools and solidifies more slowly than one with a lower ratio. This is why if you want to reduce the total solidification time, you need to try to optimize the design of your pattern if possible to have a lower volume to surface ratio. Okay? Now, to feed molten metal to the main cavity, the total solidification time for riser must be greater than the total solidification time for main cast. If you remember, we have talked about the riser rho. Okay, let us go back to the figure to show you the riser. So if you remember in your system here, okay, one very important part is the riser. And you asked me about its function. So what is the function of the riser? First, the first step in the casting process, you pour your metal. Okay, you pour your metal, and once the pouring step will end, then you have your metal filling your cavity, and it will start to solidify. But during the solidification, so now the pouring step is done. Okay, but during the solidification process, first, when you do pouring, you might have some gases entering with your molten metal, and if you don't compensate for this, you will have formation of voids in your final cast. This is why after the pouring process is done, the riser can still supply. So the riser is like a certain geometry containing molten metal. Okay, so after the pouring process is done, in order to compensate for the volume occupied by gases, molten metal will flow from the riser. This will help to escape these gases. So first, the riser will reduce the formation of voids inside my final object, final product. Second, during solidification, we have what is called shrinkage. The shrinkage process is due to the following. When you, in general, the density of solids is higher than the density of liquid. So for the same mass, when you transform from liquid to solid, you will have reduction in volume. This will lead to shrinkage of my system. Okay, so by shrinking in case of shrinking, what will happen is you will deviate a little bit from the final desired shape. Okay, in order to reduce this effect, the riser will continue to supply molten metal to fill the cavity. Okay, and in this way you can reduce the shrinkage effect during solidification. Okay, so in this case, the riser will continue to supply molten metal to close voids, okay, and to reduce shrinkage effects. And this is why we have a very important characteristic of the riser is that in order to be able to play its role, the solidification time for the riser should be higher than the solidification time for the main cavity. Because if it's not the case, if the riser molten metal will solidify before, then the riser will not be able to continue to supply molten metal to the main cavity, and it will not do its function. So we should design the riser in a way to have the total solidification time, okay, of the riser should be larger than the total solidification time of the cavity. Okay, and this is why when we design our system, we study V over A for the cavity, we study V over A for the riser, and V over A for the riser should be higher than V of A for the cavity, since CM is the same for both, okay, because we are dealing with the same casting metals, the same pouring temperatures, the same mode, okay. So in this case, in order to have T solidification riser larger than T solidification cavity, the condition is to have V over A for the riser higher than volume to surface area ratio for the cavity. Okay. So going back, so as we said, okay, to feed molten metal to the main cavity in a continuous way and ensure it until the end of the process, T total solidification for riser must be greater than T total solidification for main cavity. Now, since mold constants of riser and casting will be equal, we should design the riser to have a larger volume to area ratio so that the main casting solidifies first. This will minimize the effect of shrinkage and also will minimize the formation of voids in the final product. Now, here we will characterize shrinkage during solidification and cooling. So as we said, we have first several causes for shrinkage. So first, shrinkage is due in a first step to the large difference between pouring temperature and Wol's temperature of the mold. So when you pour, immediately after pouring, what will happen is that you will have a certain, due to the difference in temperature between the molten metal and your walls, okay, you will have what is called a shrinkage due to temperature difference, because you know that when you cool directly, what will happen is that you will have a zone for which the density will drop in a very fast way, and this will cause the transformation. If you want, you will have a solid zone directly close to the wall. Okay, this will cause a first step of shrinkage. Okay, because close to the walls you have much lower temperature. So due to this fast reduction in temperature, you will have immediate formation of a layer of solid. Okay, so you have initial solidification at mold wall, This will cause a shrinkage because, as we said, the density of a solid is higher than the density of the liquid. So for the same mass, the volume will be reduced. So this is the reduction in level will be due to liquid contraction, because a part of the liquid is transformed into a solid. Okay, and even when you cool a solid, as you cool it, its density will increase, and its volume will be reduced. Okay, so this is the shrinkage effect. Okay, and in general, the shrinkage will take place in this dimension, in the perpendicular to the cross section. Why? Because of the presence of the riser, you will still supply metal um, if you want, cover the base area will be covered continuously, and you will not have a reduction in volume from this side, because the riser will continue to supply metal in a way to maintain the constant base area. The reduction then will be in height. Okay, so in general, the shrinkage will be a reduction in height. In case not, we will specify in the problem. Okay, so we will tell you in the problem, it will be clear if shrinkage is in one dimension or in several dimensions. So this is about the first shrinkage step. Now, what is happening, as we said, okay, we have during shrinkage, we have a reduction in height and formation of shrinkage cavity caused by solidification. So in order to avoid this cavity, what is the solution? The solution is to have a riser, because when you have a riser, the riser will continuously supply molten metal, which will avoid formation of cavities due to shrinkage. Okay. Now, after this, during when we have complete solidification, okay, we have a further reduction in volume due to thermal contraction during cooling of the solid metal. So even when you reach the complete solid state, okay, when you cool, you have another period of cooling the solid. When you cool the solid, also the density will continue to increase, and when the density will increase, the volume will decrease. So we have what is called uh, thermal contraction of the solid metal. Thermal contraction is due to when we cool the liquid, when we cool the solid, its density, as we said, increases, and the volume will be decreased. This is called the second step of shrinkage. So we have two steps for shrinkage. We have liquid shrinkage and solid shrinkage. Okay. In the first step, the liquid shrinkage will be in majority of cases in height, reduction in height, because the riser will ensure to maintain a constant base area. And in the final step, when the solidification is done, we have 100% solid. Now the solid will cool, and once it will cool, now it will shrink in all dimensions. So in this case, we say it's solid thermal contraction, and in general, we give the linear percentage of contraction in the three dimensions, in all dimensions. Okay, so as you can see in this figure, in the solid thermal contraction will be multidimensional, so it will be in height, and also it will be along the base area dimensions. Okay, so this is called linear thermal contraction. Okay, and it is a contraction in the solid state, while for the first shrinkage phase, it was a reduction in liquid level. Okay, so this is if you want, we name them liquid contraction and solid contraction. Okay, so the liquid contraction is shrinkage during liquid phase, while the thermal contraction is called solid thermal contraction. It is due to shrinkage of solid phase. Now, solidification shrinkage occurs in nearly all metals because the solid phase has a higher density than the liquid phase. Thus, Solidification causes a reduction in volume per unit weight of metal. We have some exceptions. We have the cast iron with high C content, and this is why we can add graphite to iron. This will reduce shrinkage effect. So by adding C carbon during final stages to cast iron of freezing, this will cause expansion that counteracts volumetric decrease associated with phase change. So sometimes to reduce solidification shrinkage, we can add C content to cast iron. Now, concerning the shrinkage allowance, pattern makers correct for solidification shrinkage and thermal contraction by making the mold cavity oversized. So first, the riser will play a role in reducing shrinkage, but always you will have at the end shrinkage, because once you have complete solidification, you will have thermal contraction. So in order to compensate for this, when we design the pattern, we say that we will take into account that shrinkage will take place. So this is why we oversize in general the mold cavity. And the amount by which mold is made larger relative to the final casting size is called pattern shrinkage allowance. And of course, this requires special design and calculation. And the casting dimensions are expressed linearly, so allowances are applied accordingly. Okay, so we have allowances in each dimension. Now, what is directional solidification? To minimize effects of shrinkage, it is desirable for regions of the casting most distance from the liquid metal supply to freeze first, and for solidification to progress from these regions towards the riser. Thus, molten metal is continually available from risers to prevent shrinkage voids, and the term directional solidification describes this aspect of freezing and methods by which it is controlled. So what do we mean by this? So if we go back to our figure, okay, here, you can see that the riser is close to some parts and far from other parts of the main cavity. This is why we try to place the riser in a way to be close from region that will have a higher solidification time. Because to be able to, for example here, if this region has low solidification time, then it will not allow the molten metal to flow from this part to the end part of my cavity. So I should try to have the riser close to regions of high solidification time and far from regions of low solidification time. Because if this region, which is close to the riser, has a relatively low solidification time, then it will block the passage of molten metal to the remaining parts of my cavity. This is why when I put the location of my riser, I should study it in a way to be close from regions of high solidification time and far from regions of low solidification time. In this way, the regions that are far will first solidify and will not block in this way the passage of molten metal towards other regions. Sometimes we might need several risers. If we have a very complex geometry, we put several risers to be able to, if you want, supply to different zones, okay, and allow that molten metal can reach all zones in the main cavity. So the riser design is very important, and this process is called directional method because we try to ensure that all regions will be able to be accessed in order to not have formation of shrinkage cavities. Okay, so this is directional solidification. So directional solidification is achieved using Shrovinov's rule to design the casting, its orientation in the mold, and the riser system that can feed it in order to reach all regions. So we should locate sections of the casting with lower V over A ratios away from riser. So freezing occurs first in these regions, and the liquid metal supply for the rest of the casting remain open. Now, sometimes in order to ensure directional solidification, we add what is called chills. Chills are internal or external heat sinks that cause rapid freezing in certain regions of the casting. So we will see that by adding these parts, this will, if you want, allow you to easily have the past certification. So, for example, here what we can do, okay, is to just 1 second. I don't know why it rotates. Let me open it again. Okay, so here we were talking about chillers. So as you can see here, what we can do sometimes, we can add external chill. What will be the objective of this chill? External chill will encourage rapid freezing of the molten metal in a thin section of the casting. And therefore, for example, here, look, when you put the chill here, it will, if you want, as its names indicate, it will contribute to heat loss from this region, okay, because it will cool your pattern here. And in this way, what will happen is that by cooling this region, it will solidify before other regions, and this will avoid the formation of shrinkage cavity, because faster is the solidification in these zones, the better is, because in this way we will reduce shrinkage effect in the final casting product. Okay. Now, concerning the riser design, the riser is a waste metal that is separated from the casting and remelted to make more castings. So in general, riser will be trimmed at the end. Yani we will separate it from the final product. This is why to not lose metal, we can reuse it. Okay, so the metal of riser can be reused by remelting it to make more casting. In general, we try to just put the quantity that is required. Yani, once we design the riser with specific volume over A ratio, we try to choose the lowest amount quantity to not have waste, and to not have to remelt the remaining part. So lower is the remaining part, the better is. And when we try to do the design, we try to avoid a lot of excess in riser quantity. Now, to minimize waste in the unit operation, it is desirable for the volume of metal in the riser to be a minimum. So we try to have a minimum volume while ensuring maximum V over A ratio. So we should combine between these two conditions: minimum volume in order to reduce waste metal, and second criteria is to maximize V over A ratio, which will allow the riser volume to be reduced to the minimum possible value. Okay. Now, this is all about material of chapter 7. Okay. Now we will start to solve problems on this chapter together. It's already posted in problems section on Blackboard. Okay, so I will start to solve with you some problems, and after this, I can give you an assignment on this chapter, and we'll correct it after today. So, any question on this before we move to problems? Okay, so let me open a new session, and this way we start the new session with problems. Okay, yeah. So please join a new session.